Okay, so I won't go through the kind of entire content of the last lecture, but just to remind people about what we discussed. What we looked at is a little bit of gravitational wave propagation. So how do you get from the Einstein field equations to gravitational waves as a perturbation to the metric tensor? And we found that the gravitational waves, they typically stretch and squeeze space-time in the perpendicular direction to where they're traveling in. We looked a little bit at the gravitational wave detectors and how they respond and record to that stretching and squeezing of space-time. And we also took a very, very quick mini look at binary and spiral basics. So what happens when there are two black holes or two compact objects that orbit each other? And we found that they emit gravitational waves with a certain form. So that's the recap. And in this lecture, what we try to do is we'll have mostly focus on binary and spirals. So how do binaries emit gravitational waves and how do they evolve? And then at the very end, we'll look at kind of a little bit more the general picture. So what can you do with gravitational wave research in general? So let me do a reminder question, which is the same as the last one that we had in the previous lecture. So suppose that we have a binary black hole, it's orbiting. They're orbiting each other and they're emitting gravitational waves that are given by this zeroth order post-Newtonian formula. So the zeroth order correction, according to the zeroth order, the gravitational wave output is given by that formula over there. So which of these are true? All right. Yeah, so most people think that the gravitational wave amplitude is smaller at larger distances, which of course is something that we can read off from the formula over there at the top. And it's in line with the physical expectation, which is that if the gravitational wave propagates for a long time from a binary source, it goes outwards spherically, and of course, at higher distances, the signal is fainter than at small distances. The decrease in the orbital radius increases gravitational wave frequency is also true because the orbital frequency here is, according to the Kepler's formula, gm per r cubed. And of course, if you decrease the r, then you increase orbital radius. And because the gravitational wave frequency here is twice the orbital frequency, higher orbital frequency means higher gravitational wave frequency, and therefore decreasing the orbit increases the frequency. This question on the binary is always time invariant. It's a bit of a trick question because according to this formula, it is indeed time invariant. But what actually happens is that gravitational waves, because they carry energy, when the system emits gravitational waves, it draws orbital energy from the system, and because it draws orbital energy from the system, the orbital radius decreases, and because of that, the gravitational wave output increases because r becomes larger, and also the gravitational wave frequency increases. So what happens is that there's a binary and spiral. When they emit gravitational waves, the two objects lose energy, they get closer and closer together, the gravitational wave frequency increases more and more, and so does the amplitude, until the two objects merge and collide. And so it seems like people have a fairly good understanding from the last lecture on this topic. Okay, and so we said in the last lecture and here also that gravitational waves, they carry energy. And I'd like to illustrate how that process happens and explain a little bit, not in kind of excruciating detail, but to explain the basics of how do you get to gravitational wave energy. And the basic equation is always g mu nu equals 8 pi t mu nu. So the Einstein field equations. And I will be trying to be careful with my handwriting because the other feedback I got is that I tend to be a little bit fast on the writing side sometimes. So let me know if you don't understand the text. So we start with the Einstein field equations, and just like before, when we have a gravitational wave, what happens is that, of course, if we're interested in the vacuum solution, so there's no, Heinz ketchup in the universe, or there's nothing else either, then T mu nu, which describes matter, is 0. So there's no energy in the universe. The other assumption that we typically make when we look at just gravitational wave propagation is that the metric tensor is roughly Minkowskian, meaning flat space-time, plus a metric perturbation here. Now, this is exactly what we did before when we got the wave equation. And so the question would be, well, how does this help in us understanding how much energy is there in gravitational waves? And it turns out that it actually doesn't. So when we did the expansion before and got the wave equation, it turns out that it's actually not sufficient to show that gravitational waves carry energy. So why is this? The reason is that the gravitational wave energy actually comes from the second order corrections that you need to do. So essentially what we need to do is we need to expand this in terms of a perturbative expansion where lambda is a small term. We have the first term, we have the second order correction, and so forth. So people have probably done this in any QM course, but just with the metric tensors. We can do the same thing with the metric tensor. So this is G mu nu 0 plus G mu nu 1 lambda plus lambda squared G mu nu 2. So we can expand it perturbatively. And of course, this term is 0 because it's flat space-time essentially. And what happens when we put all of this again into the Einstein field equation, which is what we always do, what we end up getting is that the lambda G mu nu 1 H mu nu 1 plus lambda 2 G mu nu 1 H mu nu 2 plus G mu nu 2 H mu nu 1 is 0. So what do we have here? We essentially have the usual wave equation, which is what we looked at before. And this is the second order correction. And because we're looking at perturbative theory, these terms have to be both 0. So what we get essentially is that G mu nu 1 H mu nu 1 is equal to G mu nu 2 H mu nu 1. And it turns out that the form of this thing is the same as the original wave equation. And so the way that we can actually treat this problem is we can regard this second term as a effective stress energy tensor. So we have 8 pi g per c to the power of 4 T mu nu for gravitational waves. Now, it turns out that when we solve this system, it's actually quite difficult to define what is that there is a how much energy is in a gravitational waveform, and the reason for that is actually quite simple. It's the idea that if you have a waveform like this, then if you have a observer here, so imagine you have a point observer at this point, and then the waveform evolves, then according to general relativity, the point observer doesn't really experience any change. What it observes is that things that are around it seem to be moving. And so the way to actually define this T mu nu here, and the standard way to define the gravitational wave energy is to integrate over a larger area. So if you integrate over this thing, over some area that is larger than the gravitational wave wavelength, then in that case, you can define the stress energy tensor in a way that actually has a strict definition that is not, mutable. So what happens and what we get for the stress energy tensor is that it is basically c to the power of 4, 32 pi g dou mu. This is in the TT gauge, ij. And you get something like this. And this gives you a actual definition for the gravitational wave stress energy tensor. So how much energy is contained in a gravitational wave. Okay, so it turns out that if we are looking at, because this obviously isn't very informative to a lot of people, if you don't have kind of too much experience of what this h mu nu is and what the gravitational wave tensor is, it's usually easier to look at an example. So if we look at the example that we inspected in the last lecture and the questions, where we have a binary black hole with some masses, it turns out that we can define the T mu nu for this system in the zeroth order limit, basically meaning that we take this to be a point mass. We take, we neglect relativistic effects. And we basically assume that the Newtonian potential is, sufficiently good to set the dynamics of the system. Okay, and so if you do this, these assumptions. And again, you start with the Einstein field equations. You put the stress energy tensor such that it follows the point particle approach, so that you assume that the black holes are point particles. Then what you end up getting is that the gravitational wave emission is approximately 1/5 g over c to the power of 5 where the Iij is the moment of inertia tensors. Okay, and it turns out that this is, relatively easy to solve because we know what the moment of inertia is for a Newtonian binary system, right? I mean, you've probably solved it in, classical mechanics, some classical mechanics exercises. And what we find after doing all of this is that the gravitational wave energy that is being emitted, so dE per dt, is approximately this thing. So if I read off this formula here, you can see that there is more emission for larger masses, which makes sense when the orbital rate, angular momentum is large, then you also get larger emission. And if I also maybe expand this a little bit further still, to say that omega is gm per r cubed, then this thing becomes, let's see what it becomes. 32 gm squared m to the power of 3 per 5 c to the power of 5 r to the power of 3. Okay, and so we basically solved for a binary system. How much energy does it emit? So what does this actually mean is that the energy is taken from the orbit of the binary black hole, because there isn't really kind of too much other things that we can take it from. And because of that, the orbital energy decreases, and we get an evolving system where the two binaries are infalling towards one another over time. This happens very slowly, but the process is one of the maybe key aspects of binary dynamics. So with that information, we can go to the next question. So if you take the phones up again, then you can find the next poll, which is how much does Earth emit gravitational waves when orbiting the sun? And I can give you a bit of a hint here, which is that the omega is, of course, 1 cycle per year. So we know that the Earth goes around the sun once a year. You can use, for example, Wolfram alpha to compute this. So the possibilities is 10 times annual global power consumption, microwave oven, honeybee flight in muscle cells, which would be a few nanowatts, and well, the fourth one is that Earth does not emit gravitational waves. Okay, 4 people have answered, and there is 50-50 between a few nanowatts and a few hundred watts, so that would be a microwave. So the answer that I got, maybe some people can verify, maybe I'm wrong, but just by plugging it into the equation, I got a few hundred watts, so the microwave oven. Which would mean that, whether or not it's a few hundred watts or whether it's a, honeybee flight muscle cell, I think it's quite clear that even though Earth does emit gravitational waves, and I'm also emitting gravitational waves by, waving my hand, what actually happens is that there isn't kind of too much energy being taken away from the system. And because of that, we're not infalling into the sun. Okay. And let's move on to the next question then, which is when, hold on, was this question already here? No, I think this is a new one. So we've learned what the gravitational wave output is, which is the h. We know how much energy is drawn from the system, which is this LGW. So what happens when time goes on? So kind of this is more qualitatively when a binary object is emitting gravitational waves and it evolves, what actually happens? All right. So almost everyone thinks that the energy is drawn from the system and gravitational wave frequency increases. So I think this is very clear. Okay, so I will accept that as an answer. And the question then is that, you know, how does that process actually work in practice, and how do you model it? The long answer, of course, always is, well, you plug it into the Einstein field equations and see what happens. But of course, not all of us have a supercomputer and a sophisticated numerical software for solving things, and we'd like to get something with pen and paper. And so there is a way to solve this in practice, which is actually surprisingly simple. You know, when people kind of talk about gravitational waves and so on, of course, deriving some of these equations is very complicated, but once you obtain them, it's actually not that difficult to understand what happens to binary system and how they actually solve for them kind of in this kind of qualitative approaches. And so let's try to solve it. So we start with a binary black hole. Again, for simplicity, we say that the masses are the same. This is the orbital radius. And we have the formula. So we derived the gravitational wave emission frequency. The gravitational wave emission, the energy that the gravitational wave emits, which is the same as the energy taken from the system. But we have also something else. It's actually, you know, this is, if we think about this in terms of Newtonian approach, so we say that the orbital dynamics follow roughly Newtonian physics. So for example, if the binaries are sufficiently far away, what will always happen is that approximately the binary black hole is following a circular orbit, and also everything is Newtonian, with the addition that now we're extracting some energy. But of course, that energy extraction is a very slow process, so we can assume that at any point in time, the system is following Newtonian processes. Now, you might ask, well, hold on, Otto, you're saying that the orbit is circular, but isn't that a approximation? And it turns out that, of course, it is an approximation, but it turns out that it's a justified one, because if we have something that is non-circular, so suppose that you have a binary orbit like this, where the two black holes are following here, what happens is that there's more gravitational wave emission at these points along the trajectory. And what happens because of that is that the last orbit is changed such that it becomes closer and closer to a circular orbit. So basically, one of the results of trying to solve this system for eccentric orbits would be that the system, if it's eccentric at the beginning, becomes circularized once you have gravitational wave emission. So that's why typically we assume that sufficient time has passed on and we can assume a circular orbit. Okay, so that's simple. Now, what do we know about the Newtonian interpretation of the system? Again, point masses, circular orbit, and the gravitational wave emission, so the energy being taken away from the system, follows this the formula for the gravitational wave emission that we saw before. And so what we can do is we can take the energy, which is by virial theorem, gm squared per 2r, so gravitational wave potential energy. This is how much energy is in the system. And then, since we want to see how it evolves, what we can do is we can take the time derivative of this thing, and it is, of course, the same as minus LGW, which, if you remember the formula, it is 32 gm squared r to the power of 4, omega to the power of 6, c to the power of 4, divided by r. Sorry, there's no, this is wrong. 5c to the power of 5. Now I can see that my handwriting is not super amazing right now. And to the power of 2. Okay. All right. And so we know that the orbit decreases. So r causes r to the power of t. We don't expect the mass to decrease. You know, we have no evidence of you know, the mass being affected here. And so what we end up getting is that the gm squared per 2 equals 32 gm squared t to the power of 4 omega this thing. And you might ask, well, you know, what would happen if you had high order corrections? Well, I mean, you would get corrections to both the dynamics, and you would also get corrections to the energy being emitted, and you know, the evolution would be slightly more complicated. And well, okay, it's not slightly more complicated. It's actually something that took about 20 years for people to work theoretically, like how the binaries evolve and emit gravitational waves in high order correction. So all of this is really the zeroth order correction, but it's sufficient for cases where the binary black holes are not too close by, meaning that the fields are not that strong around the two binary black holes, and the gravitational wave emission is relatively small. But then as the orbit gets closer and closer, what happens is that you get high order corrections until eventually none of these perturbative approaches work anymore. Okay, so this is the equation that we get, and it turns out that you can actually solve that the r of t, so the orbit evolves as 2 over 16 by 5 times 2 t squared m to the power of 3 to 5 . So it doesn't matter too much. Let me maybe explain what the formula actually means. The m is the mass as usual, but then what happens is that as time goes on, we essentially get closer and closer to the two objects merging. So basically what happens is that here two objects are getting closer and closer, so the r decreases until there is a coalescence. So what does coalescence mean? It just means that two objects merge. Of course, if the two black holes touch, then you know there's nothing more to evolve. They've merged. There's nothing, you know, then it just settles into a new black hole. Okay, and so this is the way that you could model binary evolution in kind of the zeroth order term. I'll leave the high order corrections for homework. And if you wanted to ask, well, actually, let's leave it at this for now, and let's take the next question. I'll get back to the to that previous picture, but let's first take a question. So the question is, well, this is the same question as before. We'll have to skip through this one. Okay, apologies, this is a duplicate. Let's go to the next one. Okay, so we know that the we now understand a little bit about the binary evolution. So the two binaries are getting closer and closer as the system evolves. And that, of course, increases the gravitational wave frequency, as we learned before, and it also increases the gravitational wave amplitude. So they go, the frequency becomes more rapid. And if you saw the waveform, you could even extract some information from it. But a question is, how long does this process actually go on? So when does the process stop? Okay, most people think it's 4 GM per C to the power of 3, or C. Oh, sorry, this is supposed to be C to the power of 2, by the way, not C to the power of 3. There's a typo. Let me fix that. Would more people believe this result if this is C to the power of 2? It seems not many people actually voted, so it seems it's clearly not clear to everyone why this would be the case. So are there any questions on this, or anything that is there anything that would be unclear as to why it would be 4 GM per C squared?
This is the correct me if wrong. This is the event horizon or Schwarzschild radius of black hole, right?
Yes. So this would be twice the Schwarzschild radius, which, let's just say, because there is a, I realize my answer is actually slightly incorrect. Maybe someone can correct it. So the situation is this. There are two black holes, and as you said, this is the Schwarzschild radius. This is the R. So you could think of it as the size of the black hole. And I guess what you're getting at is that when the two event horizons touch, then there's a merger.
You are saying as if that is not the case?
Well, I'm not sure. What do people think? Would that be, is it a reasonable assumption?
To zeroth order, yes.
Okay, good. Yeah, I accept that. I think, if people are happy with it, then sure. Okay, so when the horizons touch, all right. Let's assume it's the case then. So the next question then is, can we actually try to model this process? So one of the questions that a lot of people might have is, for example, how long does it take for Earth to sink into the sun? So how long do we have to wait until Earth, which sends out gravitational waves at a few hundred watts, how long does it take to sink into the sun? And there's a way to model that, and it's basically very simple. So if we assume that the point when the that's strange. The point when the two objects merge is Schwarzschild radius, which is roughly 2 GM per C squared. Then we could say, okay, the merger time is equal to 2 GM per C squared, approximately, to zeroth order, right? Okay, and what we find, and let me actually put this as the T chirp. What we actually find is that the chirp time for this system is approximately 5/16 C to the power of 5 R4 g squared m to the power of 3. Okay, so you can predict where this is the r0 is the starting radius. So you basically solve the equation for when the two objects touch, and that's roughly what you get as an order of magnitude estimate. Okay, and so with that, we can go to the next question, which is when will the Hulse-Taylor binary merge? So just for the background, the Hulse-Taylor binary is the first binary pulsar that was ever discovered, and it's also the first indirect evidence of gravitational wave emission. So they noticed that this binary is actually reduced, so it will get closer and closer to each other over the years. And so the question then is, how long does it take for this system to merge? And you could compute this with how long does it take for Earth to sink into the sun or something like that as well. All right. Most people think it's I guess it's supposed to be 4.5 to the power of 10 to the power of 9 years. That's the answer that I got as well. So it will take some time before this event will ever merge and we see the gravitational waves. And so you know, if we still have people on Earth in 10 to the 9 years, I'm not sure if we're going to observe anything at that point because of expansion and things. But so that it will take some time before the thing will merge. And you could do the same computation with Earth as well, and you know, you would find that it takes even longer for Earth to observe. Okay, good. And so essentially what we have then is you know, a fairly comprehensive understanding of how binary black holes evolve and how they emit gravitational waves. And I wanted to show this this animation that we looked at in the first lecture again, but now looking at what is actually happening in here physically based on what we've learned. So here you can see, as a reminder, there are two black holes that are these 2 point objects that are orbiting each other. They are on roughly circular orbit because they've been circularized by the gravitational wave emission. They're emitting gravitational waves, so because of that, the orbital radius decreases, orbital frequency increases, and therefore the gravitational wave frequency, which is twice the orbital frequency, is also increasing. And you can see all of that down below in the waveform. And so if you inspect one of these waveforms, you can actually learn from the binary. So you can learn things about what is going on here in the binary, what kind of thing emitted it. And then you can see in a bit the merger happens, and there is this extreme curvature of space-time around the black holes, kind of represented by this canvas. The two black holes merge, and they emit the last of their spherical asymmetry away in gravitational waves. So one of the things that we also know is that whenever we have spherically symmetric system, it doesn't really emit gravitational waves. So in order for gravitational wave emission to take place, what we need is acceleration that is not spherically symmetric. Now, let me go to stop the video and go here to explain a little bit about what is actually happening. So what have we actually done in the context of this movie? So we essentially, all of this lecture is focusing on this area, which is the so-called in spiral. And we looked at the zeroth order approximation. So you could ask, well, when is the zeroth order approximation valid? Is it good for what is done, for example, here? The answer is it's good, but it depends a little bit on what you're looking for. If you want to predict the waveform precisely and look at actual data and try to predict what let's say the masses of these binary black holes are, and you know, find out kind of properties of the spins and so on. For that, it's not good enough. If you want to qualitatively understand this process and have a rough idea based on kind of this waveform frequency on what the masses of these black holes is, for that purpose, it's sufficient. So it's fairly okay for that purpose. But in reality, if you wanted to say, okay, well, I want to have a very accurate description of the waveform, you would have to go all the way back here. And so a relevant question to then ask is, well, how do you get this done correctly? So how do you actually measure how do you produce this waveform in a way that is very accurate and accurate enough for data analysis purposes? You take into account the high order correction. So we really looked at the 0th order post-Newtonian correction. Right now, I think it's, some people can correct me if I'm wrong. I think that there are post-Newtonian expansions up to the last I heard, I think 4th order. Maybe they've made some progress in there, I'm not sure. But that means that there's essentially 8 perturbative expansions up to 8 order in expansion. And the reason that this is actually quite impressive, even though it seems like the 0th order correction was very easy, is that this is a extremely accurate waveform that people can produce. The equations that are describing the in-spiral part these days is pretty much like half a page of equations. And that's the simplified version. So there is a comprehensive review on that people can read. And it took some, couple of decades of theoretical physicists working, night and day to get the full expansion. And it only works up until this point. So then the question is, well, okay, what actually happens here then? And this part is the so-called merger part. And we didn't really look into it in this lecture, but I can explain what this merger part needs. It needs numerical simulation. So what people are doing is they're essentially numerically simulating the merger process. And the idea is to connect this post-Newtonian expansion and post-Minkowskian expansion as well to this merger part. So they've made a very comprehensive set of numerical simulations, and they basically use kind of the post-Newtonian expansion to connect it to the numerical results to solve for a waveform that is phenomenological, meaning that it's not analytically solved, to create the in-spiral plus merger waveform. And then the question is, well, okay, what about this part then? And in here, this is the so-called ring down. I'm not sure if people can see this, but this part is basically black hole perturbation theory. So you can have a black hole and you add a small perturbation to it. And what you find is that there are these quasi-normal modes. So just like a bell, a black hole that is in isolation, if you kick it with a perturbation, what happens is that it emits gravitational waves, but only at certain frequencies. So it's basically like a bell. So you ring the bell and then it produces waveforms at certain frequencies. In order to figure out which of these frequencies is actually being rung, we need to look at the merger part and connect it to the ring down waveform. And so all of this is maybe some 20 to 30 years of research to produce a single waveform, and it's still active research within the LIGO collaboration and the Virgo collaboration, and there are software for producing these full waveform these days with a very easy laptop, so you don't need to do numerical simulations anymore. And the way that you can do then data analysis is kind of simple to understand. The data analysis techniques are much more complicated, but essentially once you have a waveform like this, what you do is you try to match the data. So you have an extremely accurate waveform that you can use to look for look for that waveform within the real data, and then if you can identify that the waveform is a precise match to the waveform that you have, then you have a physical description of the of this binary spiral. You can say, okay, this was whatever produced this waveform must have been a black hole with 60 solar mass component, another 60 solar mass component, and it merged at this and this time. It had this and this spin. But for that, you need very realistic waveforms. But what we've done today is basically enough to understand that the binary masses and things like that affect the frequency, which affect also the amplitude, and we can have a little bit of a understanding of where these things come from. If you want to use them for kind of estimating things in the Newtonian framework, then this is sufficient for that purpose. If you'd like to do something more complicated, then I would suggest reading up on these different expansions and possibly downloading the LIGO software for modeling the waveforms from realistic systems. Okay, so last question before we wrap things up. So based on kind of what we've learned, what kind of things of these emit gravitational waves? 4 options. That's 20 seconds to answer. Okay. Almost everyone agrees there's binary black holes Earth around the sun, which was an example. Some people agreed supernovae, and one person that is believes that the black hole moving at constant velocity would also produce gravitational waves. So it turns out that in general, any mass that is accelerating is producing gravitational waves typically, and so a black hole moving at constant velocity wouldn't be producing gravitational waves. Supernovae, however, would produce them as long as the explosion mechanism is spherically asymmetric, and so essentially these 3 answers that got the most votes would be correct. Okay, and so a little bit, a few words about the outlook. So what we really looked at is exactly one source of gravitational wave emission, which is the one that has been maybe that is in people's kind of mind the most, which is binary black holes. But there are a lot of other sources and a lot of things that people are actively researching. So one of them is supernovae, where essentially the idea is that if we can observe gravitational waves from these supernovae, then we can tell something about the explosion mechanism. So this is a very active research area, which is very heavy in numerical simulation. So a lot of people are very interested in trying to simulate these explosions. And it's taken several decades, but I think that the latest news is that it finally explodes in 3D, and there's been a lot of progress on that. So people are hoping for a detection of gravitational waves from supernovae. One of the interesting other sources is binary neutron stars. So these would be neutron stars that are colliding, and the gravitational waves that are emitted, they carry with them information about the inner structure of neutron stars. So this is something that a lot of people are interested in understanding. What kind of structure do neutron stars have, and what does that actually tell us from the about the processes kind of inside of these neutron stars. Another active area is searches for continuous waves, where if for example, a pulsar is not spherically symmetric and it emits, it rotates at high frequency, then there should be gravitational wave output. And this is one of the things that people are looking for. A kind of a future possibility would be to also have the CMB, but now actually observing it in gravitational waves. So to see kind of the starting moments of the universe in gravitational wave emission. This is a very interesting possibility for the future. One of the things that we're doing at CUHK also is, along with binary neutron star research and some supernovae research as well, is looking for gravitational lensing. So one of the things that we expect is that just like with lensing, just like with light, we can have lensing of gravitational waves, and that allows us to answer a lot of interesting questions about fundamental physics, astrophysics, and cosmology, because it gives us a complementary way to measure gravitational lensing, which is a very mature area, but this would be a new observational channel for it. And so there's a lot of research into this, where people are hoping for a detection in the near future. And lastly, there are more exotic objects that people are looking for, like wormholes and things like that. So have we seen signatures of wormholes in gravitational wave emission is one of the things that people have been investigating. And so essentially there's a lot of things to look for. And those that might be interested in some of the theory aspects, you can look into Creighton and Anderson's book on gravitational wave astronomy and data analysis. If you're more interested in kind of the data analysis aspects, so how do you actually dig out information from gravitational waves, you can look into LIGO Open Science Center. So there are some Python code examples of how to actually look for gravitational waves in data. And then if you're interested in kind of more general news, one of the areas where you can look for is the LIGO MIT LIGO Labs website. So there's a lot of the recent news out there. So essentially, a lot of rich physics to look forward to. I hope that it's been useful to look at this kind of simple binary example, and you have a bit of an idea of where these sort of things come from. I tried to make it a little bit of a flexible presentation where we go through a little bit of theory, but then have some concrete examples as well. So with that, thank you very much for listening in. And special thanks to the postgrads, Chunlung, Liu, and Ruihu. And if I'm forgetting anyone else, please tell me. But thank you very much for organizing. And if people have questions, I'd be happy to take them.
So a question here. In the very beginning, you mentioned that gravitational waves can also be used to measure H0, or the expansion speed of the universe. Is that something we can measure from just one merger event, or do we need a lot of them to compare the distance and everything?
Yeah, so that's a good question. I can show quickly the basic idea. So I'll show, well, maybe I'll say this. So basically, according to any given cosmology, you can measure DL given that you have the redshift and given that you have some cosmological model. So in here, this is a cosmology that you assume. And this is, of course, the same as the luminosity distance. So it turns out that with gravitational waves, we can measure the luminosity distance. And if we have, for example, a binary neutron star, then we can also measure the redshift. So we get this from the EM. This is kind of the simplified picture. And now you have one equation and one unknown, so cosmology, in this case, H0. And you can essentially use this. You can directly solve this equation for H0, and you would get a measurement for it. But in order for that to happen, you need to have the redshift. And normally for binary black holes, you don't get the redshift because binary black holes don't emit light unless there's an accretion disk or something like that, where some people have suggested for the 1905-21 event. There might be, but I think nobody's really confirmed it for at least the LIGO black holes, the LIGO Virgo black holes. And so if you don't have the redshift from EM, another way to get the redshift is to look at the population of black holes. So if you have black holes and they're within galaxies, and we are here on Earth, then what you can do is you can assume that binary black holes, they probably come from galaxies because they wouldn't just be in empty space. And one of the ways that you can get this redshift is to statistically assume that all the black holes trace galaxies. And if you have many events, you have enough statistics to essentially measure the cosmology, even if you don't have a precise redshift measurement. So for all of the, for a single binary black hole measurement, you would get a broad measurement from the redshift, just based on how galaxies are distributed. And that way, if you have enough events, then you have a constant cosmology, many events. And if you have enough statistics, then you can also measure H0. So there are two ways to measure it. One is that you can do it with one event, but only if you have the EM. So for example, a binary neutron star measurement, you get with a single event, you can measure H0. But then if you're using binary black holes, you need many events. So you need to use these sort of galaxy survey methodologies.
Okay, thank you. That was very fascinating.
Yeah. There any other questions?
Yes. I want to ask about the radiation power, which is proportional to the third order derivative, which is I would say quite rare, because we usually have like second order derivative thing about radiation power. Any special reason that the radiation power is like proportional to the third derivative of the moment, and the overall power of the omega is 6.
So you mean the equation in here? Is that what you mean?
Yeah, yes. I mean, it's not familiar, at least. I mean, usually you don't see physics as some kind of important quantity proportion to the third order derivative of something, because physics is all about second order differential equations. Then suddenly you have like third order derivative, and you tell me it's an important quantity. So.
Yeah, I have to admit that I don't really know the answer, if there is a good reason for that. It's let me actually see, is this correct? This is r to the power of 3. This may not be, is this correct? I may have actually written this a little bit differently. You may actually have spotted a error. Let me try to see. R to the power of -3 times 2 plus 4 is r to the power of -2. This should be -2. Does that answer the question? I think, yeah, there may be a mistake in the original formulation here.
Yeah, maybe. I mean, just kind of unfamiliar with the issue. Maybe. I mean, it's because usually physics stuff is like at most second order differential equations, so it's rare to see anything proportional to the third order of derivatives.
Oh, you mean this bit?
Yes.
You don't mean? Yeah. Okay. Yeah, that's a good question. Yeah, I can't think of a very physical argument in favor of the why there's a moment of inertia tensor that is up to third order derivative. I mean, this is basically derivative of the h mu nu to the power of 1. It's something like this. So there's a derivative of the metric tensor that I think makes sense. But I can't think of a very good physical explanation. Someone like Jolien would, or someone, I'm sure that there is someone could come up with a better answer. But I off the top of my head, I'm not sure what is the good. If there is a easy physical explanation for why we have a third order derivative. But it's a good question.
Yeah. I think I mean, follow the steps, follow the perturbation steps. You can, of course, derive this one, but it still feel a little bit unfamiliar, a little bit weird to see something is proportional to the third order derivative.
Mm-hmm. Yeah. I'm not sure if there is a good physical explanation for it, but I can try to find out. I'll get back to you then afterwards.
Okay. Thank you.
Okay. So if there's nothing else, then I think we can probably wrap things up. Thank you very much again to Chunlung, Li Yung, and Ruihu. And if I missed anyone else, thank you to them as well for organizing. I think it's really nice to see one of these initiatives. We didn't have anything like this when I was a postgrad here. And so thank you very much for that. And thanks a lot for coming in and listening to this lecture as well.